So what we're going to talk about first thing today is wrapping up our triumvirate of 3 patterns in a pattern sequence that we're going to be using to implement the ways of traversing and operating on expression trees. And we've looked already at iterator. Hopefully you have a good feeling for that. We've taken a look at visitor. Hopefully you have a good feeling for that. You'll be doing both of those in the upcoming assignments. And then the next one we're looking at that's a part of this, especially for the grad student version, is something called prototype. You've already been exposed a little bit to prototype earlier, although it probably didn't mean much to you at that point. But we're going to take a closer look at it now. And for those of you doing the grad student version of the upcoming assignments, you get a better sense of how this works. So here's a couple things to sort of talk about. First of all, remember we talked about STL iterators and how they compared and contrasted with Gang of 4 iterators. And I talked about how STL iterators have value semantics, which means that they're objects and they're passed by value, and they would use ref counters and all this other good stuff to make sure that copies are made properly, and you aren't responsible for managing the memory, much like the discussion we just had about bridge versus a pointer to a base class directly. So if you're going to implement STL Iterator Semantics, there's a bunch of things you've got to think about. One of the things you have to remember is that in C++ and in STL, by extension, there are both pre-increment and post-increment semantics. Does anybody remember off the top of your head what the difference between post and pre-increment is? Danny?
Post-increment uses pre-increment, but stores a temporary and then returns that, so that the value that it returns is before it was incremented, while the pre-increment increments and then returns the value.
So that's a very good implementation explanation. You just gave me how your code would be implemented, which is good. But what's the semantic difference? What's conceptually the difference between the two?
Well, pre-increment, it returns the incremented value, whereas post-increment returns you the original value and then increments after.
Right.
Kind of.
So post-increment defers the increment until after it's given you back the original value, whereas pre-increment first increments it and then gives you back the incremented value, as the name implies. So those are two different behaviors. Now, here's the tricky part of this. So pre-increment is easy to do. As you probably remember, if you think back to the assignment where I think you implemented this, which is probably, I think everybody implemented iterators for assignment 3B. In that particular case, then you would need to just increment the thing and then return the value. And you can return it by reference, as you see here. So here's an example where this is done. We're doing something or other to plus it, and we return star this. Everything works fine. When we try to do post-increment, things are a little trickier. And it's worth thinking through why they're trickier. So the main thing to remember is because we're using the bridge pattern, we're going to have an abstraction class that's going to have a pointer, or a ref-counted pointer, to some implementation. But we don't necessarily know in the abstraction class the specific details of that implementation. In fact, that's kind of the whole point of the pattern, is to make it so that the interface or the abstraction portion doesn't really have to know the details of the implementation portion. And yet, when you start trying to implement something like post-increment ++, you first have to make a copy of the current value, and then you have to increment, and then you have to return the copy. Well, this is a little tricky because you're in some, and we'll look at this in more detail in the next slide or so, but we're in some abstraction class that doesn't really know the details of its implementation hierarchy. And it's got to ask the implementation hierarchy to make a copy of itself somehow. So how can we do this in a way that's really clean and simple and neat? So let's take a closer look. So the whole issue here is, because we use the bridge pattern, trying to figure out how to copy the implementation is hard. Oh, and by the way, as I think we've talked about a number of times, and as hopefully you saw when you did the implementation, it always takes more to do a post-increment than it does a pre-increment. So you should get in the habit of always doing of using the pre-increment version or pre-decrement version in preference to the post-decrement version, even if it doesn't matter from the point of view of storing the side effect. OK, so here's the issue. And we could pick this for a number of things, but let's focus on iterator. So we have a bridge abstraction interface, which is the iterator interface. This is the thing that implements the STL semantics. That's what you see up there in sort of a goldish orange color. And because it uses the bridge pattern, it then has a pointer, or a ref-counted pointer, to our implementation hierarchy. And of course, as we just talked about in the context of bridge versus observer and so on, it's going to go ahead and forward to an implementation instance. So kind of here's what it looks like, right? So we've got the abstraction, and then it's going to go ahead and forward all the operations down to the appropriate subclass in the implementer hierarchy. So if we've configured this with a factor to be pre-increment, it'll forward to the pre-increment. If we've done it to the poster increment, it'll do poster increment, and so on and so forth. So the tricky question is, how do we go ahead and get a copy of the implementation? Well, you don't really know what implementation you have. In fact, that's kind of the whole point of the bridge pattern, is you don't need to know what implementation you had. But when we're trying to do STL semantics, we need a copy of the implementation we have. So rather than trying to do some convoluted runtime type identification check or whatnot, we simply make every method in our hierarchy have a clone factory method, or prototype as it's called. And when you need a copy of one of these things, you can work on it through a pointer to the base class, which is what you've got, to an iterator impl. And you simply say impl, which is just the bridge pattern, right? Impl arrow clone yourself. Now, where have you guys seen something like this before? In the clone method that you used for the queue, when you were doing the queue and the queue adapter and all that kind of stuff. You used that in order to be able to make the right type of implementation. And so what clone does is, regardless of what type this thing is, the clone pure virtual method delegates to the appropriate implementation virtual method that knows how to clone itself, because of course it knows what type it is. So it'll either be a pre-order or a post-order or an in-order and so on. But this guy here, the caller of this doesn't know, doesn't care what the subtype is. All he knows is I need to call the clone method to get a deep copy of the guy I have access to only through a pointer to a base object. So you clone yourself, you make the copy, then you do the pre-increment plus plus, and then you return the copy. Lawrence?
I know that Java, because everything inherits from object, every object has a clone method. But in C++, isn't it a little heavy overhead to have to write a clone method for each one of these subclasses?
Heavy in what sense?
In terms of you have to type it out every time.
So you're worried about the heartbreak of carpal tunnel syndrome, right? Yeah. OK, so this is a really good time to have the following discussion. Something being heavy or lightweight is always relative to what the alternatives are, right? So, is it hard or is it overkill? What's the other alternative? How else would you solve the problem? You don't have to answer that. I'm not going to put you on the spot. But whenever you're confronted with the "it's too hard" thing, the obvious response is, well, what are the alternatives, right? And it may turn out that if there's a better alternative, then by all means use that. But it may turn out that the alternatives, which in this case are somewhat clumsy and they're also they're even more cumbersome, and they don't generalize. The main problem is they don't generalize. So you could have runtime type identification. You could say, if impl is a pre-order ET iterator impl, then make a one of those. Else, if it's a post-order iterator impl, do one of those. So you could litter all this code with like runtime type checks one after another. The problem there is anytime you made a change, you'd have to go ahead and change all that code. So it's really no better than a switch statement. So the real question is it heavyweight? Well, what else were you going to do? So that's the main thing. Yeah?
Why can't we just use like assignment operator or copy constructor on the base class and have it identify?
Because how would you write the copy constructor assignment operator in the base class? It doesn't know what the subclass is at that point. It only knows what its base object is, and it has nothing, right? I mean, if you look specifically at this example, iterator impl is just a bunch of pure virtual methods. So what would the assignment operator do?
Okay, I thought it would be like a case of overloading where you passed in a certain type of the iterator.
Yeah, assignment and copy constructors don't overload in quite the way you're thinking here, because you're actually inheriting, and the assignment operators are inheriting the subclass semantics, the subclass types as their parameters, not the base class types.
Okay.
So this is actually by far the cleanest way to do it. Yeah?
So our clone method, does that just create a new object of our...
Yeah, so in the case of, let's pick on pre-order ET iterator impl, what that would do is it would say, clone would say, return new pre-order ET iterator impl open paren star this close paren. So it would use the copy constructor to make a copy of itself. It would clone itself, and it would go ahead and return that back to the caller.
Now, what does that do to our ref counter?
So it should, well, keep in mind, what is ref counted, right? So, and what you're going to do is you're going to stick this thing into an ET iterator, which itself is reference counted. That's the other cool thing here too. Take a look at this. So iterator is a type def for ET iterator, which is the abstraction class of the bridge pattern. And we're just making a copy. So we're making a new value-based iterator object with all the reference counting stuff working just like it always does. And we're sticking a new implementation into that new object, and then we're returning that by value. So that's another good reason for using the bridge pattern and using reference counting, because all that takes care of itself automatically behind the scenes without you having to worry about who owns this clone, who's going to delete the clone. You just throw it into an iterator object and return it by value, and it takes care of it properly.
So when we return temp, it updates, or when we return temp, it updates our iterator to the object that we're working on, and then it'll clean up that temporary implementation.
Yep.
Okay.
Yep. Absolutely, yes.
So it's passing temp back by value, right?
Temp is being returned by value, yes. Yeah, that's another good point. So if you remember, the other difference between pre-increment and post-increment is pre-increment can return by reference because it's not making a copy of anything. It's just returning a reference to itself, basically, after pre-incrementing it. Whereas with post-increment, you have to make a copy, and then you have to return that copy. And it has to come back by value, because if it's a temporary variable, you can't return temporaries by value. Or they'll make a copy of them, and it won't be what you want. Yeah?
If the clone method returns a new, which is like a pointer to a new allocated memory, why isn't there a memory link called this?
Because this guy it uses the ref counter or equivalent. He manages the memory, which is the whole reason why we're using, one of the three reasons in C++ that we're using the bridge pattern in the first place for these interfaces classes. Remember, the reasons are you can separate interface from implementation, you can switch implementations, and you get memory management for free, or you get reference counted memory management more or less for free. Relative to the alternatives, it's free, especially if you build a ref counter class to help you do it. And so that just basically does copy semantics. So this is also hopefully giving you yet another reason why STL and its embrace of copy semantics is so powerful, because it makes it possible to manage memory without you having to write all the nitty-gritty details yourself every time all over the place. So this is a really good trick to know. It comes in very handy. As we say here, the bridge pattern abstraction class, which in this case is ET iterator or iterator, doesn't know the details of the implementer subclass without doing all kinds of locked-in, limited runtime type identification types of things. All right, so here is the implementation interface. As you can see, what it's got here is basically a bunch of virtual methods and the clone method, as we saw before. So that's the guy that does the deep copy. And from a commonality and variability point of view, we get a common interface that can be subclassed to do different types of iterator directions, traversal orders, and so on. And we use clone to kind of move everything together. Now, it turns out this way of doing stuff, right, this little technique I showed you, which has a very, very specific motivation in the context of writing STL-style iterators for our expression tree. It's a very localized example. Actually is a broader solution to a broader problem, and it's called the prototype pattern. And the intent of the pattern is to specify the kinds of objects used to create a prototypical instance and create new objects by copying this prototype. There are some languages that are based on prototypes. So the language self is this way. JavaScript is this way. You make an object and you clone it or you prototype it to make new versions of things. So you typically use this in environments where you can't know ahead of time, or it's awkward and cumbersome to know ahead of time all the different variations and choices that you need to do. So when the classes you need to instantiate are specified at runtime, when you don't want to have a factory hierarchy, and if you want to take something that already exists and then make a copy of it rather than make a new one. So one of the other things you have to remember when you use prototype is you have to have at least one of something in order to start the whole thing rolling. If you don't have one of something, it's tough. So there typically are factories that are used to create the prototypes. Here's what the diagram looks like for the pattern. So in this case, we have a client which has some operation on it. And as you can see here, that's like our iterator. And then it goes ahead and delegates to the prototype hierarchy, which in our case is iterator impl. And then it delegates to the appropriate subclass, which in our case is the different kinds of traversal algorithms that know how to clone themselves when used in the context of an STL post-increment or post-decrement operation. Now, a couple other things to note here. If you look at this diagram, once you start looking at the gang of four, if you were to go back and kind of look at all the slides that we've talked about with the gang of four diagrams, many of the diagrams look very similar. They almost always have a very common physical shape or a virtual shape. They have something on the left-hand side that provides you an interface of some kind. There is some association, often a pointer relationship, to go from that interface to a hierarchy of things that can be customized by subclassing of a implementation hierarchy. That's typically what it looks like. So bridge looks kind of like that. Prototype looks kind of like that. Strategy looks kind of like that. Adapter looks kind of like that. There's about a half dozen, maybe more patterns in the Gang of Four book that have a very similar look. Observer even looks kind of like that. So clearly, the structure, and more specifically the structure diagram alone, is insufficient to really distinguish between different patterns. Now, there's different schools of thought on this. So colleague of mine, Wolfgang Pre, wrote a book 20 years ago called Meta Patterns. And one of his points, among other things, was that the Gang of Four book really only has 2 patterns in it. And if you think about it carefully, they all kind of devolve into a couple of different things. And so the interesting question is, first, he's probably right. There probably are really 2 meta patterns behind most of the Gang of Four stuff. And where the things differ depend on various factors, like whether the instantiation is done statically or whether it's done dynamically. Early, late binding, to use templates, to use inheritance. So those are some of the distinctions. But the other things that are important to know is it's not just the homographic shape alone that's important. It's also other dimensions like dynamic behavior. It's also things like the intent and other ways in which the roles and responsibilities in the patterns relate to each other that differentiate them from each other. In the same way that only an abstract topologist would argue that a table and a cat are the same because they both have 4 legs, right? If you look at things very abstractly, you can see, everything in life is either standing or not standing, right? Is that really a useful decomposition of life? Probably not. So in pattern world, the structure gives you a piece of the differentiation, but to really be facile with this stuff, you have to understand more variants. And the other thing that's important to note here, again, maybe a little bit more abstract than we need to make it, doesn't do much good to have only 2 of something if people can't express concisely what it is they're using at that point. So I remember once when I first became a professor at Washington University many years ago, one of my colleagues argued that we shouldn't teach Java or C++ or C in introductory programming language classes. We should only teach Turing machines because they were the most general form of computation. And given enough sand and enough rocks, you can do any kind of computation in the universe. Well, they were probably right in some very highly abstracted sense. But is that actually very useful, right? If you went to an employer to get a summer internship and they said, well, tell us a little bit about the kind of experience you have as a software developer. And you said, well, if you give me a big beach with a lot of rocks, I can do computation for you. Not entirely sure you get that internship. I guess it depends what you were trying to do. But chances are they wouldn't understand the generality. So sometimes specificity really pays off. And in particular, having the names like adapter, bridge, prototype, once you understand and own those concepts, you can converse to people much more effectively than if you start by talking at meta pattern levels of abstraction. Here's a little example kind of illustrating how this works. This is how you would implement the operator ++ post increment in C++. You would go ahead and use the clone class on the implementer hierarchy to get a deep copy without breaking the encapsulation. And here then is one example of the implementation where an object, a subclass, knows how to clone itself. So there's good and bad things. As always, anytime somebody is trying to convince you that their pattern, their solution is perfect for everything, they're either wildly inexperienced or trying to sell you something, right? By the way, we got a email from some colleagues the other day who've gone off to another university for grad school, a great university, and they were very shocked to discover at this great university, which is very famous for its research, that people there didn't take teaching very seriously. It was kind of interesting. And so they were sort of lamenting, you know, what they had stumbled upon and being very happy of the kind of thing we get at Vanderbilt, which I had that experience when I went to grad school as well. The place I went for grad school didn't really take undergrad education seriously, but I'd gone to a liberal arts school, so I had a lot of professors who actually, you know, thought about teaching and tried to help people learn. Okay, some consequences. We can add or remove classes at runtime by cloning them. You can make clones of things. You don't have to expose the lexical surface area of the subclasses. All you have to do is expose the interfaces that people see. That's a really important distinction. We'll see that later when we talk about the template method pattern, which is a pattern we'll probably get to maybe next week. So with template method, with prototype, all the developers, the client users of these things see are the base classes. That's the only thing that they have to worry about. They just say, I want an iterator impl, please, and you clone one for me. You worry about the details. They only deal with very simple things. So as a result, the surface area that you see as an application developer is minimized. It's just the abstraction. It's just the interface. All the implementation richness, different subclasses, different behaviors, it's all pushed down inside of the implementation of the prototype factory. The downsides, of course, are you have to make an object to clone it, so you may end up with extra space. For the kinds of places you typically use prototype, it's not a big deal. And you also have to be careful because if you have circular dependencies between things, they don't know how to clone each other, or they can't clone themselves. So you probably want to implement this using some kind of manager that keeps track of all the prototypes. You have to decide whether you make a shallow copy or a deep copy. If you use reference counting, you can sometimes get away with shallow copies. Otherwise, you have to make a deep copy. And of course, the other niggling issue is how do you clone all these different things with a common interface? Because the different subclasses may have different kinds of behaviors. And we'll talk a little bit more about how to do this when we talk about the strategy pattern later and how you can have a context that keeps track of diversity. Lots of examples of this stuff. Obviously, the program that you're writing here, people who are doing assignments for the grad student version, that's a good example of clone. And there are a bunch of other examples people have come up with over time. Object-oriented languages or languages and libraries and frameworks and so on that use object-oriented techniques have a tendency to use clone a lot. If you're using more of a generic programming approach, which is what you would get with a language like, or a framework or toolkit like standard template library, you don't typically have prototype-like models. You simply make direct copies, and it's done in a different way. Yeah?
So I'm confused. Is a prototype, is that a class, or is it? It's a way of arranging classes. Let's put it that way. Let's go back and look at some examples. Well, actually, let's go ahead and look at an example. Well, let's be more specific. So that's a good question. You can ask that for almost all the things we've talked about so far. So really, prototype is about how you arrange your software. A couple things come to mind. One is the concept of a hierarchy of stuff, right? So you have a hierarchy where you're using subclassing and dynamic binding or virtual functions and so on in order to be able to specialize implementations. Just a fancy way of saying we have an abstract class up here with an abstract method or virtual method, pure virtual method, and then we come down and we specialize it to make specific kinds of things that know how to make specific copies of themselves. So it's partly a method, usually called clone, but you could also make it copy me or something like that. It doesn't have to be called clone. But it's this idea that the object is responsible for making a copy of itself. That's really the key, magic secret sauce of this. And then typically there's an inheritance hierarchy, and somebody else needs to work on these objects without knowing the details of how they're actually implemented, but they want to work on the results of having them copy themselves. So that's the idea. Abstracting away, copying, making it somebody else's responsibility to know how it works, just using the results. Those are some of the sort of meta patterns, meta themes you see in this pattern and other ones as well. Yeah?
Does this pattern just have parts of it that are very close to the bridge pattern, or is that actually a bridge pattern inside of this?
Oh, great question. So what's the relationship between this and bridge? So first of all, if we were to go back, we won't do this, but if we were to go back and look at the Gang of Four book opening slides, remember we divided the world up into like creational patterns, structural patterns, and behavioral patterns. So bridge in the Gang of Four book way of looking at things is a structural pattern. It's about how you arrange, it's how you separate interface from implementation. That's the way they cast that. Prototype was filed under creational pattern. So it's about how you make things. So that's one distinction. Prototype is about making stuff. Bridge is about how you expose an implementation to a client through an abstract common interface and stable interface. So they play different roles in terms of their purpose and purpose. Another way they differ, if you take a look at this, is that remember the bridge pattern, you had a client with a method called foo, and then it followed a pointer to a subclass instance, and it delegated or forwarded the method to the foo method. So I, as a user, would call foo here, and that would then go ahead and call foo down there. With prototype, in contrast, the client has some operation, right? Like in our case, we're trying to do operator plus plus on the Stl Iterator, Stl Stl Iterator. And as part of that operation, it needs a copy of whatever the thing is it's pointing to. So when you call this method, it's not forwarding that method down here. It's using the clone method to make a copy of the thing that it points to. So it's got a different purpose. It's not being used for the same thing. Now, as we saw in this particular example, we have the bridge pattern. So going back over here, this is another good example of pattern compounds. ET iterator is the bridge pattern because we basically have things like operator plus plus, which are being forwarded to the appropriate implementation methods that are part of the hierarchy. And the bridge implementation, one method in the bridge implementation, uses the prototype pattern to clone the subclass, the appropriate subclass, in order to fulfill its semantics. So that's an example of where we use prototype as part of the bridge implementation.
Will it often be coupled like that, or one also?
Depends on how far you push it. So people who are very pattern savvy, we'll say, pattern literate, for lack of a better term, their software over time starts to exhibit what I call high pattern density. And you'll see this when we get a little further along in the expression tree example. What you end up with is pretty much in a well thought out, well designed object oriented program developed according to patterns. Almost everything in there was done for a reason, and the reason almost always reflects back on some role in some pattern. And oftentimes those roles and those things intersect, right? So in this particular case, this method, operator plus plus, is an interface method in the bridge pattern, but it's using the clone method in the prototype pattern to do its thing, right? So that's bridge and clone. So you'll often find, many parts of the programs have reasons for why they exist in the way they exist because people are applying the patterns. But that's kind of, a more advanced form of pattern literacy, again, for lack of a better term. When I write software now, I try to use patterns everywhere just because that's the way I've come to think about it. But other people might or might not find that useful if they don't understand the patterns. For example, if you hoist, and maybe this goes back to Lawrence's earlier point, if you foist on somebody about a design that's full of composites and builders and prototypes and all this kind of stuff, and they have absolutely no clue what these patterns mean, then at some level their initial job is a little harder. Because now they've got a lot of stuff, right? Whereas before they might have had one file or two files. Now they've got 25 files. Is that hard or not? Well, it depends. It depends what your background is. I'll give you another good analogy. You've been using make in this class. And the purpose of make is to be able to ensure that things that depend on each other stay in sync when some things change, right? So in your case, in the case we're using make, you have a bunch of source files, and you have an object, you have a binary or an executable that depends on those source files. And if you make any changes to certain files, then you'd like to make sure that when you type make, those files that have been changed get recompiled, and anything that depend on those files also get recompiled. And you want to have your final executable correct and consistent relative to the current version of make. Now, is that complicated? Well, let's think of what the world would be like if you didn't have make, or pick your favorite source code management tool. It doesn't have to be make, but or build dependency management tool. If you didn't have make, how would you write your program if you didn't have a tool like make? What would you do? If you were worried about getting out of sync between your source and your binary executables. You'd put it all in one file. Exactly. Very good. So, and why would you do that? So when you compiled that one file, you'd never have to think to yourself, did I forget to compile this file? Did I? It would always be consistent. Now, what's the obvious downside of putting it all in one file? It's all in one file, right? So, which is fine when your program is 20 lines long. If you have 20 million lines, if you have healthcare.gov, maybe that's why the website didn't work. They put it all in one file. I don't know. But the point is, if you have lots of people working together on lots of files, putting it all in one file is not a useful thing to do, right? So the minute you have more than one of something, you've traded one set of problems for another, right? You've traded the I've got everything in one file and it takes forever to compile problem for the, oh crap, how do I keep things in sync problem? So what does make do? Make keeps it in sync. Now, the point there is that because you have a tool that automates stuff, you can, with relative confidence, create lots of files. And as long as you're willing to learn the obscure syntax of make, or whatever tool you use, enough to keep track of things, then whenever you make new files, you just add them to your make file, and away you go. It all works fine. But if you didn't have that automated tool, you probably wouldn't come up with a solution that allowed you to have lots and lots and lots of files. And the same thing is true with design and design patterns. If you didn't understand the design patterns, you'd be unlikely to end up with things like 20 files, one for every subclass of component node, because it wouldn't make any sense. You'd be like, why do I have 20 files? This is confusing. The minute you understand the composite pattern, then when you look at those 20 files, you go, oh yeah, those are the different subclasses of the expression tree nodes. There's a one-to-one mapping between what I understand at the design level, as reflected in my diagrams and the way I explain people in terms of patterns, and the representation of those things in terms of code. So once you understand the patterns, you can be more sophisticated in your designs. But if you don't understand the patterns, you're going to have a hard time. OK, so to summarize this section, this has been a big section, important with a lot of moving parts. We combined 3 patterns plus a few more, as you saw. Actually, we have probably more like 4 or 5 patterns here altogether. We use iterator in order to be able to get to every element in our expression tree, and not just every element in any particular order, but in particular orders, right? In order, post order, pre-order, and in order, and so on. So we used iterator for that. We used the bridge pattern in order to be able to abstract how we access those things. Because we used the bridge pattern, that required us to use prototype to know how to make clones of these things. And we did all this stuff so we would have a way to abstract traversing through every element in the tree. And then as we got each element, we could then go ahead and apply some operation to it. And we wanted to do this in a way that was open-ended, so we wouldn't hard code the operations into what the tree was doing. And to do that, of course, we used the visitor pattern. Now again, there's other things we haven't really talked about, things like factories and so on, and we'll look at those later. But that's basically where we stand at the moment in terms of the patterns. Any questions about any of that stuff? Now, what you get to, in real life, people typically don't just hand you a well-thought-out design, unless you're lucky and work on a project with experienced architects. But they typically don't just hand you a pattern-oriented design. Your job as you get further into this whole wonderful world of software is to learn how to do this on your own so that you can figure out how to recognize the design elements, identify the patterns to use, and so on. But we have to start somewhere, and this is a good place to start. OK, let me give you an overview of what we're going to cover next, and then we're going to go ahead and take the quiz. So at this point, we have covered patterns for tree structure and access, namely composite and bridge, tree creation, namely interpreter and builder, tree traversal, namely iterator, visitor, and prototype. So we've got over a half dozen patterns so far, all hopefully well motivated and understandable that you can implement for your assignments. The next things we're going to do is talk about how we interact with our expression tree from a command point of view, how we tell it to do various kinds of things, and we'll explain why we do that and so on. And then we'll also talk about how we create stuff and we create things using factories. Factories are very important. You'll be using them a lot in what you're doing. So that's what we're going to cover next. Just in terms of the grand scheme of things, let me go ahead and skip ahead a little bit, show you what's coming. So we have command and abstract factory and factory method, which are patterns that work together in a whole part relationship. Then we're going to talk about how we order the execution of the commands using state-oriented protocols. This is a pretty interesting discussion, probably the most complicated part of all the pieces. And then we're going to go ahead and talk about how you structure the application. And we'll talk about something called the reactor, which is a non-gang of 4 pattern for a change. It deals with event handling. And then we're going to talk about a couple more patterns. We're going to talk about accessing global resources using singleton. You've already seen that before. And then we're going to wrap up finally with strategy and template method, which are really patterns for dealing with variability in your design space. So again, by the time we're done, we'll have gone through about half of the patterns in the Gang 4 book. Not that there aren't other ones to do, but we'll eventually run out of time in the class. Any questions? OK, let's go ahead then and do the quiz.